All right, so here you have a graph of e to the x. We're going to graph the derivative. There is not a critical point. It never actually goes truly horizontal. It's going to get closer and closer and closer and closer to being horizontal, but never actually get there. Now, don't draw this all over your graph, or I guess you can if you want to. But if I start drawing in tangent lines, do you see how they have very shallow slopes, like very tiny? And then if I draw in more tangent lines, do you see how the slopes get steeper and steeper and steeper and steeper? So when you graph the derivative, it's going to start out very, very, very small and then get bigger and bigger and bigger and bigger and bigger. I actually taught you this one already. The derivative of e to the x is e to the x. Okay, so we're going to go to our bubble sheet. Pick one of your bubbles that's left. Doesn't really matter which one. The derivative of e to the x is e to the x. Now, do you remember when we talked about the arc trig? And I said, I'm covering it, but this is not like a super heavy topic and you might need to decide what to let go. I'm going to also show you what you'll do if it's a base other than e. So like if you had 2 to the x or 5 to the x, like, do you know what number e is, like roundabout? 2.7. If you know it's a number, I'm really happy. If you know it's 2.7 something, I'm thrilled. Okay, but it's a number. If you have something else, I'm going to show you what that is. Again, they may throw 1 on the multiple choice. I'm covering it for you. It will still be itself. It's almost kind of like a chain rule. Not really technically a chain rule, but you're going to multiply on ln of whatever that number is. So for example, do you need to step out and cough? Okay. So for example, if you had 3 to the x, the derivative would be 3 to the x times ln of 3. It's not hard, but it's one more thing to have to remember. So, there you go. All right, so let's try these first couple of problems. I like to teach you a rule, do a few problems. So looking at number 1 here, the derivative of 3e to the x is 3e to the x. The 3 is kind of just there. The derivative of e to the x is e to the x. There's just a 3. It's my favorite one. It's just the best. What'd you say? Now, what rule would you need for this one? Good product. Identifying what rule you need is honestly half the battle. You can figure out what rule it's supposed to be. You're usually good because after that, it's just the matter of doing said rule. All right, so it would be the first thing times derivative of the second, which would be e to the x. So it kind of looks like you didn't do anything. That is the one thing that does kind of trip people up sometimes is it looks like nothing happened. We did do a derivative, all right? Plus the second thing times derivative of the first, which would be what? 2x. Cool. Making sure you guys are all right. All right, what rule would you need for number 3? Chain rule, good. So the outside function is e, the insides or the guts is the 4x squared. So you do the derivative of the outside first, which is just itself. Hey, Ms. Cole, looks like you just copied the problem. Yep. And then you chain on the derivative of said guts, which would be what? 8x, good. I heard a wait. Are we okay? Or did we let it sink in? All right, what rule for number 4? I try to throw like one of each of the other rules in there because those aren't gone. All right, if you remember where it stops, or excuse me, if you remember where it starts, you will probably be good. It starts with the denominator times derivative of the numerator, which is 2. If you're ahead of me, hold on, because I'm going to write this one a little bit differently to show you something. All right, minus the numerator times derivative of the denominator. Now that involves another rule. Good. It is itself, and then you're going to chain on the derivative of 5x, which is just 5, over the denominator squared. Now, can I show you something? Instead of writing it as squared, I'm just going to write it twice. Do you remember no cancellation without factorization? Okay, but this one you could factor and cancel because e is its own derivative, so it gets very repetitive. Do you see how there's an e to the 5x in this first term? Minus, do you see how there's an e to the 5x in this one? And then, so you actually can cancel one of them out because if you factored this out, then it would cancel because it's in all three of them. Short answer, please don't. Now, what you would need to do to continue simplifying this would be distribute the 5 through there, distribute the negative sign, but that's algebra 1 stuff, and I'm not gonna, like, are you okay? You can distribute, deal with negatives, I'm just trusting you. All right, and then number 5 is what I was saying, if it's something other than e.
On that last one, can we only do it with e to the x? Is that the only time we could cancel?
It's common. It's more common with that because e is its own derivative, so it shows up in both of the parts of the numerators. So like yeah, it'll happen with e. Sometimes it happens with, it kind of just depends on what you have. I'm sorry, that's kind of a crap answer, but with higher level math, sometimes you just have to see what you get.
Yeah.
A lot of the time. I know that's like a non-answer, but with e it happens because it gets repetitive. So do you see how this one's not e? It's 7. Okay, so it's gonna be itself just like e. And then there's a chain rule. You would chain on what for your chain rule? 2x, the derivative of x squared. And then you just multiply on an ln of whatever that base number is. So in this case, 7. Again, it's not hard, but it is one more thing to remember. So, you know, I showed it to you. It is not super likely to come up, but that's how you do. I have seen them in the multiple choice. They might throw you one. But that's E. That's it. That like E is like a 5-minute lesson. That's all it is because it's itself. All right, so scoot back up here to the LN graph. This is your graph of LN. I'm going to draw in some tangent lines. You can if you want, if you don't want to destroy your picture, but just to illustrate it for you. Do you see how these slopes are very, very steep? And then they're going to become less and less and less steep. Will they ever actually be 0? No. So it's going to start out very, very big and come down almost to 0, but not quite. Now, it is a little tricky, but usually if I wait my class out, somebody comes up with what that is the graph of. It is what? It is rational. Do you see how this side is missing? Why is this side missing? Like, why don't I have this piece of it? Yeah, ln doesn't have any graph over there. All right, but it is your rational graph. Good job. Gold star. All right, so go over to your bubble sheet. Your derivative of ln is rational, 1 over x. I don't like how I wrote that, so I'm going to write it again. 1 over x. And again, not super likely to come up, but I'm not going to be accused of, she didn't teach that to us. So I'm going to show you what it looks like if it's a different logarithm. So instead of ln, which is base e, if you have a log base a. So like if it was log base 5 of x, you get what I'm saying? Like a different number. It's the same thing we did with the exponential, except instead of multiplying on ln of a, you multiply on 1 over ln of a. So it's still going to be 1 over x, but then you multiply that on. Again, that's not difficult, but it's one more thing to remember. So I showed it to you. It's not likely to come up. I think if one of these was going to come up, it would be the exponential one. I don't think you're going to see this, but again, I don't like to leave anything out. I like to show you it all. Bless you. So let's do a couple of the LN ones and then I'll give you your halfway through break. So we'll just do a few of these. I don't know. We'll see until I feel like we've done enough and then we'll take a break. All right. So for this one, derivative of ln of x is 1 over x. It's your rational. There just happens to be a 4. So what do you think? Yeah, 4 over x. The 4 is just there. It's kind of like when we did 1 over 2 square root. There's be 4 over 2 square root. Just like the 4 is just there. That's all that there is to that. Maybe we'll do like this section here in a minute. Take a break. All right, what rule do you need for 7? Product. 2x cubed is the first thing. ln of x is the second thing. So product rule is the first thing times derivative of the second, which would be 1 over x. Kind of just memorization. Plus the second thing. And then times the derivative of the first. What would that give us? 6x squared. Now, again, I'm trying to just teach you calculus and not algebra. The algebra is an assumed skill, but how could you rewrite this first term? If you have an x cubed divided by an x, it would be 2x to the second. So like in a multiple choice scenario, that's how that first term would look. Okay. This one, there's not anything you can do to that. This is not a product rule. That's the really common mistake. And I get totally why that happens. What rule is this? It's chain rule. It's not ln of x times something else. It's ln of that stuff. Okay. So your derivative of ln, the rule says 1 over x, but it's 1 over all of that. Like 1 over whatever's there. And then you chain on the derivative of that stuff. Now, instead of putting a dot and putting it off to the side, if it was a multiple choice question, where would they put that part? If they would put it in the numerator. So what is the derivative of the guts of it? Yep. Perfect. Now, what they'll do a lot of times, this one doesn't, but they will make it turn out to something that factors, and then you have to cancel out. Do you know what I'm talking about? Like factor and cancel out? All right, so number 9, what rule do we need for that? Quotient rule. All right, so again, if you get where it starts, I also threw some trig in there, but I gave you the easiest one. All right, so denominator times derivative of the numerator. That involves a chain rule. It's not 1 over x, it's 1 over that stuff, because it's more than just x. But weirdly, because it's rational, what are you going to chain on? Well, what's the derivative of 2x? 2. So with ln, it just ends up canceling because the derivative is rational. And then when you do the chain rule, like, do you see how these 2's are just going to go away anyway? We're not going to simplify it, so it doesn't matter. But denominator, derivative of the numerator, minus what comes next? Numerator, good job. Derivative of the denominator, which is, good job, over. And that means the squared comes in between the sign and the x because you are squaring the sign function, not just the x. Or, I know some of you asked me about it, can I put parentheses around sign and then a squared? That means the same thing, so you're fine. And then I threw one on here that was a different base, just so you could see, you know, what it looks like. It's going to be the same thing as ln to start out with. You're going to put 1 over whatever's there. And then you're going to chain on, chain rule, the derivative of that stuff. You could put a dot and put it off to the side. I'm going to just put it in the numerator. What would that give us? Derivative of 10x squared. 20x. And the only difference is you multiply on 1 over ln of whatever the number was, which is 3. So again, you just have to slam that in the end. It's, again, not difficult, but one more thing to remember. But I showed it to you. If anyone was like, hey, were you taught that? You were. All right. What rule is this one? Chain rule. And how many links in the chain? 3. What's the most outside one? The cubed, the 3. Then inside that is cotangent. And then inside that, e to the x. Okay, so the first step, you bring the 3 down. Good. Everything else stays the same. You drop it to a 2, everything else stays the same. What I usually do at that point is try to cover up the 3 because people want to like do something else with that. We already did it. Now we're on cotangent. First of all, it's a co. So what does that tell us? Negative, good. Derivative of cotangent is negative. Good job. Cosecant squared of that stuff. The stuff doesn't change. Remember, the guts doesn't. I almost wrote x too. I had to erase it. I was like, oh yeah, there's more. All right, and then you chain on the derivative of e to the x, which is e to the x, which is great. Believe it or not, that's all one entity. There's nothing added or subtracted. That is all one term. This is the same kind of problem. How many links in the chain? 3. And I'm going to start over here because it's going to get real long. Secant got hungry and ate ln, which got hungry and ate 4x. So you start with the most outside. Oh, I erased my derivative of secant. Secant tangent of all the stuff. All right. So it's going to be secant ln 4x tangent ln 4x. Derivative of secant is secant tangent. You just keep all the stuff. The stuff does not change. All right. Next function is ln. So 1 over 4x, brilliant. And then you would multiply on the derivative of 4x, which is 4. And the 4s would cancel. That's going to happen because the derivative of ln is rational. But anyway, that's how that works. So actually, the answer in multiple choice, they would probably write all of this stuff over x. Do you see that? Like they would probably put all of that stuff over x is how that would look. This one looks super fun, right? No. Hold on. Let's talk about what rules this would involve. It would involve chain rule. This would be a product rule inside of a quotient rule and with another chain rule right there. I'm going to show you a different method. It is going, pep talk, it's going to involve your log properties from last year, which you can act like you weren't taught, but I taught about half of you, and I know that you learned them, okay? So notice I did not write a prime mark on that. I'm not doing the derivative. We're just going to rewrite this. I'm going to write the first term and see if it jogs anyone's memories. It would be 2 ln of x.
Oh, okay.
Hold on, let me write the second one and see if it brings anything else back. It would be plus 1/2 ln x minus 1.
Okay.
Yeah.
Okay.
Hold on, let me get everybody there. Is it jogging anyone's memory though? I'm seeing heads nodding. You would put the 2 down out front, just ln of x. Why is this plus? Multiplying. In the numerator is positive, denominator is negative. Why is there a 1/2? Square root ln x minus 1. And then it's going to be minus ln 3x plus 4. That denominator didn't have a power, so there just isn't one. How on earth did that make it better? Well, you can now do this as 3 totally separate problems instead of one huge monster problem. Okay, we broke it into bite-sized pieces. So now I'm going to do derivative. This is where you can put in a prime. What's your derivative of 2 ln x? 2 over x. Good. Plus, let me cover up the 1/2. The derivative of this would be 1 over x minus 1, right? There's just a 1/2 there. The 1/2 just stays. So it's 1 over x minus 1. The 1/2 just stays. If anyone who is a very thorough person noticed, what other rule technically happens there, but we don't have to write anything? There's a chain rule, but what's your derivative of x minus 1? The insides. 1. So do you want to write times 1? You can if you want to. I just wouldn't. All right. Minus, it would be 1 over 3x plus 4. And there's one other thing. Chain on a 3. Now those 3s don't cancel. Why is that? No cancellation, not factorization. Okay, you cannot cancel this. And then this is your answer.
Perfect.
So you break it into like bite-sized pieces, basically. Yeah. Yeah, you can leave a 1 here and then put chain rule dot and a 3. That comes down to personal preference of how you want to write it. All right, I'm throwing some vocabulary at you. What do we need for an equation? Yeah, a slope and a point. And our point of tangency is e squared, which remember is a number. That's 2.7 squared. That's a number. You just don't get a calculator, so it's whatever. How do I get the output value? Plug it in. All right, look at e squared cubed. How'd you get 6? You multiply. Power to a power means you multiply. 2 times 3 is 6. Did I lose anybody there? Okay. And then if you do ln of e squared, it would look like this. What do you think? It would be 2. If you were with me, we played a lot of Quizlet. ln and e are inverses. They cancel out. So I wouldn't write e to the 6 times 2. I would probably write 2e to the 6. Can you all be quiet while I recap that? Because I feel like I lost a few of you. All right. When we plugged in e squared to the 3rd is e to the 6. 2 times 3 is 6. And then when you plug in e squared here, ln and e cancel. It's just 2. I just didn't want to write it in this order, so I wrote it the other way around. Okay. Now we're going to do the derivative. What rule do we need? Products. That is the first thing. That is the second thing. I'm not going to say it all because I feel like that's getting annoying, mean talking at you. If I write out this answer, can you guys try it and we'll make sure we get the same thing? First derivative of the second plus second derivative of the first. Yeah.
Why is it like 1 square? When the
Yeah, but the rule is that you take the exponent and write it out front. So it's 2 times 1. This does come out to 1, but it's not 1 squared. It's 2 times 1. Does that help? Okay. Log rules are just, and you got shortchanged on that because you did pre-calc condensed into a half of the year. So like willing to give more leeway. All right, is this what you all got? Cool, I'm not hearing complaining. How could you rewrite this piece of it? X squared, good. Okay, what are we gonna plug into this delightful thing here? E squared, good. So if we plug in e squared, you know what? I'm gonna have to write a little bit smaller. I'm using up too much of my space here. We plug in e squared squared, e to the 4th, very good, plus ln e squared is just 2. And then this would be 3e squared. So 3e to the 4th. You're going to be okay, I promise. This would be what? 6e to the 4th plus 1e to the 4th is 7e to the 4th, which is a number. It's 2.7 to the 4th times 7. I just don't know what that is without a calculator, but that is a number, okay? But it doesn't matter. This is your point. That's your slope. Go with it. Don't discriminate, okay? Your answer is going to be y minus 2e to the, go with it. Just trust the process, equals 7e to the 4th, parenthesis, x minus e squared. Welcome to advanced math. Those are all numbers. They're just values. All right. The last thing I'm going to teach you, we're going to finish our bubble sheet today, guys. Go to your last bubble. All right. This is your inverse derivatives. Oh, I guess I didn't title that. If you want to title this bubble exponential and logarithmic, I'm sorry, I didn't title that one. I apologize. I am very type A like that too, so I probably should have done exponential and logarithmic. This one was trig. All the others have titles. Okay, good. We're good now. Inverses. You know how in general rules in math look horrible until you put some actual numbers in them and then it starts to make sense? The inverse derivative rule is so complicated looking that I don't even show it. I just give an example with actual numbers. Because it will just literally confuse everyone. It even confuses me. So I'm like, we're not doing this. I just do it with numbers. So I do an example. When you get an inverse function, which do you know the notation for an inverse? It's f with a little -1. That means inverse. What you want to do is make a table for x, f, and f prime. So your input, your output, and your derivative. And then make another little table for the inverse and the inverse derivative. If you don't like this notation, I'm 100% on your side. I don't really like that either. It's f inverse prime. It's the derivative inverse. But that's what it is. So accept it and move on. I've had to do that too. I don't like it either. I feel like it looks weird. So I'm just going to show you how this works with actual numbers. Give me some single digit numbers and we'll fill it out. All right, so 2, 1. If this function has the point 2, 1, the inverse has the point 1, 2. And then give me a different single digit number. We'll do 3. I didn't really want it to be 1, 2, 3, but that's okay. If this is 3, this inverse derivative is 1/3. All you do is flip it over. Reciprocate, I should say. So it's very, very simple, but when you write it out in general terms, it looks just awful. So I just always teach it as an example. Okay. So let's just try a couple of these. I think I just have 2 of these on here. So you're given this equation. Find the inverse derivative at 6. So when they bring up an inverse, what you want to do is make your 2 little tables. I actually kind of don't mind these. It's like a scavenger hunt, and you're trying to find all the numbers to fill in. You're just trying to gather all of the information. Oh, at the end of the year, after the AP exam, one of the games we play is a scavenger hunt. I send you out into the school to like find stuff. Oh, but you know what? It's not going to work this year. Because I would have people take pictures and videos of the things they found. And you can? Okay. I was going to be disappointed. Okay, so you're going to start with this number. You want to find the inverse derivative at 6. That means 6 goes here, and whatever lands in this box is our answer. You want the inverse derivative at 6. Do you see how I placed the 6 there? Now, if 6 goes there on x, where can I put 6 on this chart? Good, because inverse means you're swapping them. That allows you to set up a problem. That's where you're like, okay, I can start doing something. I can take this function and set it equal to 6. And then we're going to do some algebra. Evacuate. Do you remember that? Evacuate. That's what I call it because people want to try and go from there. And I'm like, you have to evacuate. What do I mean when I say evacuate? Those are understand my, yeah, move it over. So it all equals 0. So you're going to subtract over that 6 so that it equals 0. We're going to factor it. So make your Algebra 2 teacher proud. It'll be 2x and 1x. You make your pre-calc teacher proud. We did this last year too. What is that going to go like this? 3 and 2? Yeah, because then the outsides will be -4. Insides will be +3. Cool. What is this factor going to give you? -3/2. I don't want that one because the problem says greater than 0. Okay, so I don't want that one. Instead, I want 2. So this graph has the point 2, 6. That means this graph has the point 6, 2. That's not really important for the answer, but I like to put it in there just so I filled in everything. Okay, but you don't technically need that number. Now we're ready to get a derivative. So we're going to find f prime. This is the easiest part of the whole problem. You want the derivative of this. It's not a product rule, a quotient rule, a chain rule. It's not trig. It's not e. It's not ln. It is literally just do this derivative. So what does that give us? -1. Good. That all usually goes fine. Here is the step that gets people. Do you want to plug in the 2 or do you want to plug in the 6? Well, you're trying to get this answer, so you would want to plug in 2. In multiple choice, one of the wrong answers will be if you plugged this in instead, I guarantee it. Okay, but you want to plug in 2. So if you plug in 2 to that, what are you going to get? 7. And so your answer to the whole thing is 1, 7. Cool. Last one. It says inverse derivative, so make your little charts, tables. I don't know what I'm going to call them. This is encroaching on my space, so I'm going to erase it and move it over. After you make your tables, try and figure out where you want to put that 4. Needed to leave some space to do this one. What column is the 4 going to go into? Yeah, it's your input for your inverse function, which means it's also going to go right here. If it's the input over here, it's the output over here. That allows you to set up a problem. You're going to set this thing equal to 4. I'm going to be really honest. You can do a whole mess of algebra, but it's only 4. That means the numbers are going to stay pretty small. I think the answer is probably 1 or 2. Try plugging in 1 or 2 to this and see if it comes out to 4. That's honestly what I would do if I was doing the problem. Is it 2? Because 2 squared is 4 over 1. Okay, do you see how that was a lot faster and easier than trying to do a whole messy algebra problem with a fraction in it? Guess and check is always valid. I do it a lot. So where else does 2 go? Yep, your inverse. Again, that's not really important to the answer, but it's technically true. I like to have it all filled in, right? Whatever lands here is our answer. Now, what rule do we need for this derivative? Quotient. Okay, so it is the denominator. Here, I'm going to stop saying it. You guys just do it too, and I'll make sure we get the same thing. Going to be fine. You all did that great on your quiz. Like you listened to me when I explained quotient rule, you studied, you got it right. It's fine. If you had your numerator backwards, that's fine. You can fix it for the test. Like that's a simple thing, right? You guys were all fine there. Here is the tricky part. Are you going to plug in 2 or are you going to plug in 4? Good. It's your X value right here. If you plug in 2, let's see, that's just going to be 1. So this will be 4 minus 4, which would actually, if the numerator is 0, then the whole thing is 0. Oh, I remember this problem now. It's actually kind of interesting. I think I did this on purpose so we could have a conversation about it. You can't reciprocate 0. So what is your answer? Undefined. Do you remember in the unit circle, when you would end up with zeros, but you had to flip them, we put undefined? And what does that mean is in the graph? Ask them to. Good job.